This is the answer key for homework number 8, FIN499, Spring 2019. The tab labeled Returns gives us daily data on the Russell 2000 index for the last 30-some years. The Russell 2000 is a small cap index. These are the firms that rank from number 1,000 to number 3,000 in size. For each day, I took that day's price divided by the previous day's price minus 1, and that gives me the return. I'm going to go ahead and assign a name range to these values so that I can use the name range later. So I'm going to highlight the entire set of returns, and you'll notice I did not include the header at the top in that range. I only want the data itself, and I'll go to Formulas, Name Manager, and define a new name. We'll call it Return. Excel actually looked up there and saw the word at the top and assigned that to them. So now I can simply use the word return instead of cell references for these ranges of data. Task 1 asks you to calculate the descriptive statistics on the Russell 2000 index and put your output into cell 20 below, A20 below. So let's do that. We'll go to Data, Data Analysis, and we'll get the descriptive statistics. I've given you some hints here. I can simply type in the word return since I defined a name range. There is no label in the first row of my data. Recall that I left out the label in the data itself. For the output range, I'm going to put it right here in cell A20. And then we need to check the boxes for a few things down here. Okay, we'll go ahead and click OK, and Excel will calculate our descriptive statistics for us. I'm going to do a little formatting on these numbers here. Don't need quite that many decimal places, just clean things up a little bit. Oops, wrong way. Maybe we'll give them 4 decimal places. The count's always an integer. I'll leave that as is and go to 4 decimal places here also. Okay, let's see what it asks us to do. It says calculate the descriptive statistics. We've done that. It says build a 95% confidence interval for the population mean. Our sample mean is 0.0004. We'll use that sample mean plus the standard error to calculate our confidence interval. So I see a typo here. Nope, it's not. Yep. The second thing we need to do is build a 95% confidence interval. So we'll come down here, we'll set this cell equal to the standard error. We'll multiply that by 1.96. So that tells us that the population mean is within 0.00283 of the sample mean. So we'll take the sample mean and subtract 1.96 standard errors. Then we'll take the sample mean and we'll add 1.96 standard errors. This is our 95% confidence interval. That means we're 95% confident that the population mean is between 0.0008 and between 0.00064. Note this range does not include 0, so we are 95% confident that the mean is not 0, that it's something other than 0. This concludes part 2. Let's have a look at part 3. It says, based on the kurtosis, does the distribution have more extreme values than would be expected in a normal distribution? The kurtosis is 7.9. This value is greater than 0, and so we would conclude that there are more extreme values than we would expect if it were a normal distribution. So Kurtosis is greater than 0. Therefore, there are more outliers. That is, more extreme tail values. So this distribution has more values in the tails than it would be if it were a true normal distribution. Finally, we look at the skewness. The skewness here is negative. When you have a negative skewness, oops, let's try again. Our skewness is less than 0. Therefore, it's skewed left. This means we have more extreme values in the left tail of the distribution than in the right tail. Okay, this concludes task number 1. Task number 2 asks us to prepare a histogram of the returns on the Russell 2000 index. The original copy of this had a typo here. It said the S&P 600 index, and that's one I had used in a prior semester. It says use the frequency function as an array formula. So let's see how we do this. So first I did this. Let's see how many bends we need and how wide they need to be and so forth. So typically we use about 20 bends when we're preparing a histogram. We could have more or less, but this is a reasonable value. We also need to know what's the minimum and maximum values in our data set. So here I have the minimum of my returns. Recall I named a data range earlier called return. And here's my maximum return. So the minimum is about minus 12.5% and the maximum is a little over 9%. If we wanted to make 20 bends, starting at minus 0.12 and going up to 0.09, those bends would be about 0.01 or 1% apart. So here's what I did. I come over here and create my first bend. It needs to be a little bit lower than my minimum of negative 12.5. So I set it at negative 13, and then I incremented by 1%. So each subsequent bend is 1% higher than the previous one. And then my last bend needs to be a little bit higher than the maximum of my data set, so I went up to 10% for the highest bend. So I created these by hand, simply the first number lower than the minimum of my data set, and the last number a little bit higher than the maximum of my data set. Okay, so let's go ahead and calculate or prepare the histogram using the frequency function. So here's how we do it. Put the cursor in cell B15, hold down the shift key, and use the down arrow to highlight the range. Then we click in the formula bar and we type equals frequency. There it is. We have to tell it what our data array is. The data is my return data, and since I've already given it a name, called it return, there it is right there. And then I tell it where my bends are. And my bends are right here. We'll close our parentheses, and then we have to press a special keystroke combination to get the array formula. We cannot press the enter key. Instead, we must hold down the control key, hold down the shift key, and then press enter. When we do that, Excel counts the number of return observations in each one of these bend ranges. We can see that most of our returns are here around 0. A few positive, quite a few positive in the 1% range, etc. When we plot this data, we end up with the distribution over here. This concludes task number 2. In task number 3, we're going to use the histogram tool built into Excel's data analysis. In this case, we're going to leave the bin range blank and put our output in cell A10 down here. So let's do that. We'll click here. We'll go Data, Data Analysis, Histogram. We'll click OK and fill in our boxes as needed. For the input range, I'm going to use my returns. The bin range I'm going to leave blank. And the output I'm going to put on this worksheet right here in cell A10. Finally, I'm going to chart the output, and that'll give us our histogram itself. We'll click OK and let Excel go to work. Excel has created its own set of bins. These are not formatted as decimals. Let's go ahead and do that, or rather as percentages. Home, percent, maybe give them 1 or 2 decimal places. So Excel did something similar to what we did in task 2. Here I started my bins at negative 13% and they go up to 10%. If we leave the bin range blank, Excel will use the minimum from our data set as the first and the maximum of our data set as the last. Okay. It prepares a histogram, looks similar to what we did. We'll expand this a little bit so we can see it better. So there's the histogram. Unfortunately, Excel doesn't do a good job when we leave the bin range blank of using nice round numbers here for our bin borders. And so we see fractional values down here also. Notice these numbers are not nearly as clean as what we see here. Nice round integers. This concludes task number 3. In task number 4, we are again going to use the histogram tool that's built into Excel. This time I created the bins myself. You'll recall that here we did not use the histogram tool. I used the frequency function that's built into Excel as an array formula. In task 3, we let Excel create the bins and we get unusual values for the bin borders. And so in task number 4, I'm going to create those bins myself. Again, the first one is a little bit less than negative 12%. The last one a little bit bigger than 9%. We look down here. Okay, so let's go for it. It says we want to put our output here in cell C15. So we'll go to Data, Data Analysis, and Histogram. We've got our return data already put in. Our bin range is here. We don't have labels in our data, so we'll leave that unchecked. And for the output range, we're going to put it in cell C15. Alrighty. We'll chart the output and let Excel do its thing. So you'll notice that Excel has reproduced our bins right here that we already had, and it's counted the number of observations in each one of those bins. So sure enough, Excel finds the same answer we did. Using the frequency function, we found that there were 3173 in the 1% bin, and we see the same number here. Excel's also created a chart for us. We'll stretch it out a little bit and get our nice chart. Notice that when we use these nice round numbers for the bins, we get the same thing on the x-axis here. In task 3, we let Excel create the bins, and we get kind of non-nice round numbers here. This concludes task number 4. In task number 5, I ask you to prepare a histogram of the returns on the Russell 2000 index using a pivot table and a pivot chart. I ask you to put that pivot table here in cell 10. To prepare our pivot table, we'll click Insert, Pivot Table. I could type in the word return here since we had named a range, but it's nicer if we have a label at the top. So I'm going to go ahead and select the data by hand here. I'll just go back here and click on the word return, Control-Shift down arrow, and highlight all the data. It's going to put it in cell A10 of our task number 5 spreadsheet. So we have our pivot table and our data is labeled return. That's why I went in and selected that data by hand and gave it the label. Okay, what we're going to do is drop the return into the rows. What it does is create essentially an observation for each day. Not exactly. If we have 2 days with the exact same return, we'd only have one line in the table for them. But other than that, it's pretty much one observation per day. The problem is there are thousands of them. We have 7,948 here. So we need to group our data somehow. Let's click inside of here. Any observation, it doesn't matter which one, and right-click on it and group our data. Excel has provided us with some default values, and we'll notice that the first one is minus 0.1253. That's the minimum of our data set. Let's use a nice round number here. Let's use minus 0.13, or negative 13%. Then the ending value is 0.0926. That's simply the maximum observation in our data set. We'll round up to 0.10, and we're going to increment by 0.01, or 1%. So it'll create bins for us from negative 13% to positive 10%, incrementing by 1%. There we go. So it's just collapsed our data. It's still all there. They just grouped them together into these ranges. So we have our bins now. What we need to do next is count how many observations are in each bin, similar to what we see here. Let's pick this one. It's a little bit better. Okay, so we need to count the number of observations in each bin. We'll do that. We'll come over here and drop the return into the sum of values box. And you'll notice it's default to count, which is what we want in this case. So sure enough, we have the exact same number of observations in this bin that we saw before, between 0 and 1% returns. Now we can create our pivot chart. We click on Insert. We come over here to Pivot Chart, and it guesses that we want a clustered column, which is exactly what we want. So we'll go ahead and click OK, and here's our pivot chart and histogram as created by Excel. One of the problems we run into when using Excel is these round-offs. Our bins are not exactly 0.01 apart, and so we're getting these tiny little round-off errors that result in very strange looking numbers here. So this is 8.7 times 10 to the minus 18th power. So strange numbers. There's no way to fix the formatting here. These are actually text cells. These are not numbers. They look like numbers, but they're text as far as Excel is concerned. So we can't use the formatting buttons up here at the top of the page to fix them. It's as good as it gets if we're using the pivot table and pivot chart to prepare a histogram. It's quick and easy, but the results aren't real clean down here. This concludes task number 5. Task number 6 is some practice generating random numbers. So we're going to use the RandBetween function and generate random numbers between 0 and 100. And we'll copy this formula down to the rest of the green cells. So we get about 100 observations here, it looks like. Okay, so our numbers are all between 0 and 100. I guess I could create a box here for min and max, and we'd find that the min is at least 0 and the max is at most 100. I calculated our standard deviation. Should be somewhere around 50, and it is. Next, excuse me, the average is around 50, not the standard deviation. Next, we're going to use the random number generator built into Excel. One thing to notice, these numbers are dynamic. Every time I press the F9 key, the spreadsheet would recalculate and these numbers would all change. Over here, we're going to generate some normally distributed random numbers with a mean of 12 and a standard deviation of 30. So let's do that. So we're going to go Data, Data Analysis, and scroll down to the random number generator. There it is. Okay. So how many variables? We have one variable with 100 observations or 100 random numbers created. We're going to use a normal distribution. And again, we're going to make our mean or average 12% and our standard deviation 30%. We're going to put that output in this cell right here. We'll click OK and see what Excel does. It's now generated a bunch of random numbers for it. We know that it wiped out our cell formatting there. I can fix that back real quick. Let's see what we have here. How about this and this? Get our numbers back, and then we'll make them percentages. and maybe give them a couple of decimal places. Okay, so each one of these numbers is a random number from a distribution with a mean of 12 and a standard deviation of 30. This is the sample mean, so our sample mean's 11.5, very close to the 12% mean, population mean that we specified. And our sample standard deviation is 32, again close to our population standard deviation of 30. Here's a distribution or histogram. Looks kind of like a normal distribution, which is what it's supposed to, because we used a random number generator with normal output. This concludes task number 6. In task number 7, we'll get some practice using the linear regression tool built into Excel and interpreting the output of that regression result. Okay, let's see what we have here. We're going to try to explain the return on a stock using 3 variables, the PE ratio, the market cap, and a dummy variable. In this case, the dummy variable takes on a value of 0 if last year's return were negative, and a 1 if they're positive. There is some evidence that there's momentum in stock prices, and so if a firm had a high return last year, they tend to have a high return again this year, and vice versa. So we'll go ahead and run our linear regression. We'll click on Data, Data Analysis, and then pick the regression tool. We need to tell it where our data is. The Y range is the return data. I'm going to include the label here and check the box for labels. Then, for our X range, scroll back up, we have 3 X variables, PE ratio, market cap, and dummy, and then we'll highlight all of these as our X range. We have labels at the top of each column, so we'll leave that labels button checked. And then let's see where we want to put our regression output. Let's see, put your output in cell F20. So we're going to put our output in cell F20 right here. Oops, cell F20. And that's all we need to do. We'll go ahead and click OK, and Excel will run the linear regression and give us the results. So here are the results. Let's work on interpreting. I'll clean things up a little bit here. You don't need so many decimal places, it makes it hard to read. Okay, put 4 decimal places. Let's go with 4 here also. So change these to 4. There we go. All right. Now it's time to interpret the results of the regression output. Let's see what we have here. We have an R-squared of about 0.51. So we can explain about half of the return simply by knowing the values of these 3 variables. We get an F-test, which is less than 1% in this case. It's 2 1,000ths. And so we have a very small F significance score. That means we would reject the null that this group of variables cannot explain the return. And we conclude that these are significant. They do help explain the return. What we're really after are these numbers down here. Let's have a look at these. We'll ignore the intercept. That tells us the average return for a stock with 0 PE, 0 market cap, and 0 on the dummy. Well, there's no firms with 0 market cap and 0 PE, so it's an out-of-sample observation, hard to interpret. Let's go directly to the PE ratio. This is our slope coefficient. It tells us how much the return changes if the PE ratio increases by 1. So as the PE ratio goes up, the return goes down. The slope coefficient for the PE ratio is here, and so we can interpret it as follows. It says, if the PE ratio increases by 1, on average the return increases by a negative amount. So returns go down as the PE ratio goes up. Our p-value on the PE ratio is 0.01, just under 1%. So that is significant at the 5% level. In other words, we would reject the null that the PE ratio does not influence return and accept the alternative. The PE does affect our return. And in fact, it decreases our return. Let's get the slope coefficient for market cap. It's down here. And the p-value for the market cap. This tells us the slope coefficient. It's the change in the y variable. The y variable is return for a 1 unit change in the x variable. The x variable is our market cap. So if the market cap increases by 1, the return increases by 0.00048. However, our p-value is a bit large here. It's more than 5%. And so this is not significant. In this case, we would not reject the null and conclude that the null is valid. That is, that the market cap does not affect return. Finally, we'll get the dummy variable. Its slope coefficient is 0.018. And the p-value is 0.2655. So that p-value is much higher than 5%. I could format these as percent if you prefer to look at them that way. So we have a nice small p-value here, low probability of being wrong when we reject the null, and a very high p-value here. We're definitely not going to reject the null, and this is not significant. So we have no evidence that the dummy variable affects returns, and the dummy variable is whether last year's returns were positive or negative. So knowing whether returns were positive or negative last year does not help us predict returns in the following year. Let's see what comment I have in this cell. It says we interpret the slope here as the extra return earned by those stocks with a dummy value of 1 relative to those with a dummy value of 0. However, it's not statistically significant. So even though the number itself is not 0, it's not significantly different from 0. Okay, this concludes task number 7 and homework number 8.